I want to introduce you to Zhengjing Yang, Senior Data Scientist at Databricks, Eng Kwon, also at Databricks, Staff Software Engineer. I'm not sure I pronounced those names correctly, but
good enough.
Thank you. So we're going to talk today about scaling data workloads using the best of the both worlds.
Good morning, everyone. My name is Cheng-Yin Eng. I'm a senior data scientist at Databricks. I help customers implement scalable and production-ready ML solutions.
Yeah, I'm Hyuk-Jin Kwon, staff software engineer in Databricks, and then I'm the top contributor in Apache Spark. So if you have any question about that, I'm happy to answer later.
Yeah, so today we'd like to share with you from our respective data science and also software engineering backgrounds some tips about how to scale your data workloads. Whether it's debugging your errors and also it comes down to debugging your performance issues as well. So today there are two main topics really, and they tackle the two sides of the same coin. And the first side is talking about how you can change almost nothing in your Pandas code and scale it up to run on a distributed cluster. The second side of the same coin is now that if you were to run on Spark, how do you then add your own custom Pandas API to leverage that familiarity? And then we'll wrap up the talk by introducing to you a new tool called Spark Connect that allows you to run Spark everywhere more easily. This is an undeniable statement. We use this every day, probably in our data workloads, and they are so widely integrated in numerous Python libraries, matplotlib, scikit-learn, etc. But really, there's really one problem. And my computer science professor used to joke that if you have no questions to ask at any classes or any talks, just ask this question and you instantly become the smartest person in the room. So the problem is really about scalability, right? How do we scale using Pandas code? So of course, the first easy thing to do is to simply throw a bigger and bigger instance, whether it's a CPU, whether it's a GPU, and hopefully it just works. But at some point, you will reach the point where you are no longer satisfactory with the performance, and you hope to do something better. So then the next naive thing to do is to downsample data simply. But I think a lot of the data practitioners in the room will agree with me that data is so precious. Why should I toss them away? So we don't want to do that. So that leaves us with no choice but to actually link to other distributed processing framework. And there are multiple of them out there, but today we'll cover Spark. Spark, as you can see, is open source since a very long time ago. And there are multiple language support as well, including SQL and Scala and also R. And today we'll mainly focus on PySpark, right? How do we interface with Spark using Python? And so you can see as the years go by since it was open source, the popularity of PySpark has also pretty much increasing as well. So what is Spark? This is a fundamental distributed processing engine. And if you remember nothing from this talk about Spark, I just want you to remember one thing. It has one driver, and it can have multiple number of worker nodes. And this concept of multiple worker nodes is actually really important because each worker node can hold a subset of data, which is also commonly known as data partition. And so the driver will then be able to distribute the workload across the worker nodes. And then the worker nodes, like all of us, we execute the task that we're given, and then we report back to the driver. So that's the fundamental architecture of Spark, a driver and a multiple worker nodes. But of course, we have to learn a new syntax. Nobody likes doing that. And you can see that at the very top right here, we have a Pandas code snippet. And then this code snippet, all it does is to filter data where rows have quantity that's more than 10. Right? And then you see the code snippet on the the bottom over here. There's pretty much no similarity. We have to learn how to build a Spark session and then learn how to actually write our select statements. You no longer use the .lock or .ilock in Pandas anymore. But beyond just the surface level API difference, there is also fundamental differences in how Spark data frames and Pandas data frames are implemented. So let's take a look. So for Spark data frame, it is not mutable. So what that means is that because Spark data frames are fundamentally built upon RDDs, which stands for Resilient Distributed Data Set, once it is constructed, it's no longer being changed. So it means that when you add a new column, or maybe when you cast a column type differently, what Spark does under the hood is to create an entirely different RDD object. And of course, it's distributed, whereas for Pandas data frame, even if you throw it a distributed cluster with huge number of worker nodes, Pandas is only going to run on the driver. Because Spark data frames are distributed, there is no concept of indexes nor row orders as well. And this is actually a topic that we'll dive into a little bit more about when we convert one into Spark data frame to PySpark data frame, how do we actually make them communicate to each other? So the last property over here is evaluation. And this is probably one of the most important properties that make Spark data frames fast. So in Spark data frames, there's a notion of lazy evaluation. It means that all Spark transformations are actually not executed unless you call an action command. So things like filter statements, your select statements, those are all lazy. They're not eagerly evaluated until Spark has a chance to come up with an optimized logical plan behind the scene, and then you trigger an action, which is maybe something like a count command, and then the execution would run. Whereas Pandas data frames evaluates everything eagerly. So what if you don't want to learn Spark? This is where pyspark.pandas come in. Some of you may have heard about the Koalas project before that we announced in 2019. It has been officially integrated into the PySpark environment, the library, in 2021, and hence the name pyspark.pandas. So what this does is really unifying both syntaxes from Spark and then to Pandas. So you can see in this code snippet right now, I am just simply commenting out the top line of import statement. Import pandas as PD, I replace it with import pyspark.pandas as PS. And you can see then I am still using my .log pandas API in my code. I pretty much just changed the import from PD to PS, and this works, which is great. It means that now I no longer need to learn a new syntax, and yet I can leverage the distributed processing power. So how does it work? It seems like magic, which is great because then you and I actually don't really need to know about the implementation detail. But just to give you a very high level to perhaps intrigue your appetite, pyspark.pandas provides this lean API layer that sits on top of Spark and Pandas. So to communicate between like PySpark Pandas and also to Spark data frame, there's something called an internal frame that's basically acting as a communication bridge between the both. So this internal frame will hold all the metadata of Spark data frames, and it also holds the mapping from the PySpark Pandas data frame to Spark data frames as well. So it means that when we make changes to PySpark Pandas data frame, the internal frame would decide whether or not it should create a new state or whether it should copy a new state so that the immutable property of PySpark data frames are still preserved. Now, many of you might be wondering about the performance because it seems like it's too good to be true that we don't need to actually change any syntax. So let's take a look at the distributed framework over the cluster over here first. So you don't really need to know the numbers, even if you can't read them. So across each group, we have a different benchmark task, all the way from calculating standard deviation to join and accounting count. But you can notice that within each orange dotted box, you can see the downward trend. So for each bar that you see, the blue, orange, and green goes from 64 nodes to 256 nodes. The takeaway is that as we linearly increase this number of nodes, we see that the performance actually almost linearly gets better as well. Hence, you see the downward trend across the benchmark tasks. And the good performance also exists in single node cluster too. So you can see for the blue bar, it represents Pandas. And then for orange bar represents the Pandas API on Spark, which is what we abbreviate as Spark.pandas. You can also see the orange bar is consistently lower than the blue bars. So it also works very well on a single node cluster compared to Pandas. So why should you start maybe switching to PySpark.pandas or considering doing it? You can see the API coverage is really increasing very steadily across the years. And we started from Koala 0.1, and now we're in PySpark 3.3. So there are three. We divided the API coverage by different groups, data frames, series, and indexes. Now we're hovering right at around 70 to 80%. And just that, this number is actually really good, and it will never really reach 100% because some single node functions just don't make sense to be converted to a distributed processing method. So we don't expect 100% coverage. So what is the first best practice we're going to share? So we mentioned something about the indexes. The difference between PySpark and Pandas is in that Pandas data frames has indexes, whereas PySpark doesn't. So let's talk about the pyspark.pandas. What are some indexes that we can actually choose? So the first one is sequence. Sequence means that you are implementing the index that increases one by one. And this is actually the least performant index choice because it forces all of your data to run on a single node because your index needs to be increased one by one, that it needs to know some order. So we should absolutely avoid this when data is large. The second index, which is distributed sequence, means that we're still implementing the index increase by one, but it's for each group. So it is better than sequence when the data is large. The third one, though, is the best performing one for the index choice. It means that we actually don't need the index to be increasing one by one. It can maybe jump from 1 to 3, to 9, and so on. And the index is indeterministic. So this helps because you no longer need to force the order of the rows to be always exactly the same. So it means that when you actually convert your data frame to pyspark.pandas, the index choice is actually something you need to pay close attention to. Now, should you learn PySpark or pyspark.pandas? Have I convinced anyone to not learn PySpark yet? Or that's not my task over here, but it's really to help you understand when it's best to use either. So if you were to know, if you are really familiar with Pandas already and you want to just scale out your analysis and your task is strictly restricted to only data analysis, then pyspark.pandas is a really good choice. But we know that Spark is more capable than just doing data analysis. It actually also does data streaming as well, for example, and graph processing. So if your use cases span outside data analytics and include streaming and include graph processing, then you should still learn PySpark. Now let me turn it over to Hyojin to discuss, once you have your Spark code, if you were to know Spark already, how do you then implement your Pandas Function API on top?
Thanks, Jingyi. All right, so we talked about the Pandas API on Spark just now, but what if you want to work together with other libraries? Like let's say you need Pandas native instance, and you want to work with the scikit-learn, then we have some friends, Pandas friends in PySpark. So in case of the Pandas API on Spark, we compose Pandas API on the top of the data frame. But these friends, it works together with PySpark, and then it handles the Pandas native instance. So there are two APIs that's supported in PySpark. The first one is Pandas UDF, and then the second one is the Pandas Function API. So the Pandas UDF is actually an expression. You can think is that it's like column-wise operation. And then whereas Pandas Function API is actually a query plan under the hood. So you can think it's that like table-wise operation. So Pandas UDF, it works consistently with other expressions, and then Scala UDF or like regular Python UDF. And then you decorate it with Pandas UDF. Whereas Pandas Function API, there are some API defined under the data frame. So you invoke that to use that. Here's the actual example. So the top one, the Pandas UDF, you decorate your function that deals with, for instance, here, Pandas. And then the second one, it deals with the Pandas data frame because it's table-wise operation. All right, let's talk a little bit more about the Pandas UDF. So the Pandas UDF, you must annotate which type you want to take as an input and output. So, and then the PySpark will decide how to execute by reading the type hints. So for instance, here I type the Pandas service as an input and output. Then the PySpark will decide, and then it will transform, and then it will perform a scalar operation. There are serialized, deserialized, and then executed in the vectorized manner. And then it will leverage the NumPy under the hood when actually it's executed. So this is the 3 examples. The first one, as I just mentioned, since I typed Pandas series as an input and output, it transformed the values. And then the second one is the aggregation example. So you take the Pandas series, and then it outputs the primitive type. So here I performed the sum, so I performed the aggregation. And the last one, in PySpark, we have nested types. For instance, struct type. This struct type is converted to the Pandas data frame. So you can convert that Pandas data frame to the Pandas series. In case of Pandas Function API, of course, you can optionally annotate the type, but it matters which API you invoke. And then the PySpark will decide how to execute them based on which API you invoke. Pandas UDF and Functions API, they are all actually share the same in-name execution logic. So they are both serialized, deserialized, and executed in vectorized manner too. So in the example below here, I invoked map in Pandas, right? But the Pandas UDF shares the same API, but Pandas Function API, it depends on which API you call. Let's take a look at the example. So the first one, I group by, and then I apply in Pandas, right? And then here, each group will be a data frame, of a Pandas data frame. And then the subtract mean will be operated. In case of the second example, I perform the group by with cogroup. And then it will take the 2 data frame. And then each group of individual data frame will be converted into the function, into, for instance, here left and right. And the last example is that the map in Pandas. So this is similar with the Ardidis map partitions. So basically, you're applying the function in batch. So this iterator of Pandas data frame will be actually one partition under the hood. This is an example of ML. Cheng-Ying has a better insight in ML, so she will briefly explain the example.
Yeah, so in ML, it's very common for us to have forecasting use cases. And these forecasting use cases are usually specialized by store or maybe by a specific state and etc. Right? So here, I want to revisit the concept first. Like in really a Pandas function, you can write whatever you want. Right? So this is an example of me writing whatever I want in my train function that literally trains a random forest classifier model, and then it predicts the output and then calculate the model performance for each device ID. So this is an example of what if I have many device IDs, many devices, I want to actually predict maybe the rate of mechanical failure. And typically, I maybe have 2 choices. One is to maybe write a really long for loop and just loop through each unique ID and then train a different machine learning model. Or maybe I could just duplicate my notebook and then just pass in a different subset of data frame every single time, right? So, but that is actually very cumbersome. So here, you can see that there's no Spark code in here. It's really just nice data frame. It returns that schema that has basically 3 columns: a device ID, number of training samples used in model training, and then lastly, the model performance in AUC metric. So I pass in this function to my group by apply in Pandas. So you can see that this removes the need of writing for loops or duplicating the code. And this works very well even in production too. So we have multiple use cases across different industries that uses this group by apply in Pandas to be able to apply to the forecasting use cases.
Thanks. There is a common problem when you play with the Pandas Functions API or UDF. You might see some out-of-memory issue. especially when you perform a group by and then apply in Pandas. Since one group is in the memory, the group of the Pandas data frame will be in the memory, so you might face the out of memory. And then there's a common technique that is basically sorting. But I mean, that's sorting, but basically you're adding the one column, like hash column-ish, and then you separate group into the smaller group. So let's take a look at the left table. And then here I added this sort column. And then in the second table, the group A has actually separated into two because of the sort. And then I can operate the group by again based on the call. And then it will show the final result. So basically it's two-phase group by. And how to do it in codes? Let's say the first example here, I'm grouping by one column, right? And then let's say the data is skewed, and then the one group is like huge, so it's all in the memory. Then it might, out of memory. I convert that to code to I added the sort column in the second example. So I group by first, and that will separate the big group into multiple groups, and then that output I will group by again, and then I aggregate. It's like sort of partial aggregate technique-ish. So you can avoid out of memory by sorting. What about debug and performance? So how to debug the implementation errors? Make sure it works on a single node, because your function should work in the single node. And then try to distribute it in Spark. And if you're using iterators like map in Pandas, make sure use the Python closures or nested functions instead of one big function that is difficult to debug or difficult to profile. Make sure your functions are optimized. Don't excessively use for loop. There are many other techniques, for instance, factorization by leveraging the NumPy. So I better don't use a lot of for loops. Make sure your data is properly partitioned. PySpark itself provides a lot of partitioning APIs, for instance, repartition. So you make sure you have enough partitions so it can be distributed and then executed in parallel manner. Use your Spark UI to debug performance issues. Add print, and go to the job tab and stage tab and check the standard input and standard output and errors. All right, so we talked about the Pandas friends in PySpark. This sort of additional section, the Spark Connect. In current PySpark development, the Spark community is putting effort to implement the Spark Connect. And this is also closely related to the Pandas UDF and the Pandas Function API. I will start with the general problem that Spark has. So the Spark is often associated with the data center itself. So in the cluster, your Spark driver will in your Spark cluster together. So your application logic works within your Spark cluster. It's not your laptop. So if you zoom in the Spark driver, which is basically, you can think that it's Spark client. The Spark driver, the client, although it's client driver, it does lots of things. It has your application logic, and then it has a catalyster, and it dispatches your task into the cluster, and it has a little bit of distributed execution logic, for instance, code generation. So it's pretty heavy, and they are all very coupled together each other. And then the problem is that the modern applications do not match with the current Spark structure. For instance, you want to do the debug and then develop in the interactive shell or IDE. This heavy one big driver should come together within your laptop, for instance. And then the other language supports are difficult. Yes, there are some language support existent now, but they all are very implemented in a very complicated manner, because you have to implement the JVM access logic by yourself. And then edge devices like Raspberry Pi or in your browser or your iPad, this big Spark driver cannot run in those devices. So how do we deal with this problem right now? For the modern applications, we just send a SQL string or JDBC. The Apache Spark support the Drift server that supports like JDBC or ODBC. So it takes the SQL string or JDBC request, and then it addresses those requests. For Jupyter or IDE, there are some existing solutions, for instance, Apache Libby. But under the hood, they send the quotes in string to the server, and then you get the output. So you cannot really add a breakpoint and then debug. And the other language support, as I just mentioned, they're implemented in a very complicated manner. Spark Connect itself resolved that problem by decoupling the API layer to the front. So it will create a sort of protobuf message, and then it will ask the driver to execute the job. So the applications is very thin, because what it does is that just it constructs the message and then ask the Spark driver to execute the job. So it can address IDE or other language support very easily. Let's take a look at the implementation detail quickly. So the dataframe API, Scala or Java or Python, they all share the SQL module under the hood. And then the SQL module is actually consisting of the logical plan. And then this logical plan is optimized or with lots of techniques, for instance, predicate pushdown or column printing, and then it will be executed. Spark Connect client will construct this logical plan before the optimization, which is unresolved logical plan. And then it will just send to the Spark driver server. And then the Spark driver will execute those jobs, and then it will send the result back to the Spark remote client side in arrow format. So by doing that, you can leverage the power of Apache Spark everywhere. As I just mentioned, you can use it in the IDE, like Jupyter very easily. I will show you a bit of example later. And then since it just constructs the message, right? So other language can implement this client layer very easily. And of course, we now in Spark 3.4, we added the SQL support in Python. And then in the master branch, in the next Spark version, we'll have the full support of Pandas API on Spark, and Python UDF, structured streaming, ML, and then they will be all available in the next Spark version. All right, so this is the simple example. I just want to show you just the simple idea, like how it works. So I just run the Jupyter server in my laptop locally. And then what I need to do is I just pip install PySpark. And then I can just ship the existing logic right away. And then I can easily work together with existing BI tool. This is just simply just show the idea. I didn't have to set up like Apache Libby or Jupyter Enterprise. I just pip install and that's it. This is another example of Spark Connect. So I'm using IDE with separating the computation to the cluster. So here I can see the DF, data frame, and then the result. Based on the result, I can execute other jobs. I can see the schema here, or I can perform other operations, like for instance, count to see how many data is inside. The result is a bit slow now, but we will show. Yeah. So you can run the job very easily with IDE, and then interactively debug. You can run everywhere within your browser or Raspberry Pi. It's very light, so it can even work in like Node.js nodes or like browser anywhere, and then it will show the pretty chart like this very easily, without doing the computation of all the optimization or scheduling the task within your browser. All right, that's what we prepared so far. If you have any questions, I'm happy to answer.
Hi, great talk. I'm super excited. I had a quick question because a lot of the times when I'm putting together forecasts, I don't have just one dimensional variable that I'm grouping by. So, instead of just being items, I might be looking at an item, a customer, and a DC combination. And obviously there's like a specific order that I would want to separate those out in. So how does Spark handle that, especially in the ML context?
Yeah, so if you were to have multiple groups, multiple columns you need to group by, then it means you will just pass in more columns in the group by. Yeah.
So you're specifying the group by in like your Pandas function
yes.
or like the PySpark Pandas function?
So
Because
it
I
will
didn't see you
be-
specify dimensional columns in that example. So that's why I was curious.
Yeah, so in this case, when we have multiple columns, we actually don't need to change anything in this pandas code right here because this assumes that we are running this code on each group already. So and then on this, in this example, we apply this function on a group instance, right? So Spark df.groupBy is a group instance, and then we assume that this group instance will capture all your groups. So if you were to have more than one group, then you would add an additional column within this group by statement, and then the train my model would still apply on that particular, like basically set of groups that you have supplied.
Gotcha. Perfect. Thank you.
Thank you. I have a question about Pandas UDF and Python UDF. So what's the difference between these two? Because in theory, in Python UDF, you can also use Pandas, right? So what's the difference between these two?
Yes, so we are going to share the same code path soon.
Yeah, so yeah.
What you said is all correct. Yeah, we will share the same code path under the hood in the next Spark version. Meaning that, yeah, what you said is correct. Yeah, it shares the same. Currently, it's separate code path because Pandas UDF came out later. So it's vectorized operation, but it leverages the vectorized operation. But yes, we are working on making sharing the same code path.
Yeah, so it means that Python UDFs are executing the code row at a time. But Pandas UDF has another name, which is vectorized UDF. And that means that you can execute a function batches at a time. So in Spark, the default settings, you can actually set the maximum records per batch that you can process each time. I believe the default number is 10,000. So if you were to use Pandas UDF or vectorized UDF, compared to using UDF, you should see a performance boost because of that max records per batch setting.
Thank you. That makes sense. I have a follow-up question about that. For Pandas UDF, do you use the PySpark Pandas API under the hood, which means it will be kind of infinitely scalable, or you use the normal kind of Pandas implementation, in-memory implementation?
So you mean in the context of Pandas Function API, whether or not we're using Pandas API, or are we actually converting to pyspark.pandas?
Yeah, that's my question.
It is using Pandas API.
Yes.
Sorry, last question. So for this PySpark Pandas data frame, is there any concept of ordering? I see indices, but no ordering, right?
We have, it is not by default, but we have an option to support the ordering. So it will have to sort by default. But it is because that PySpark itself doesn't guarantee the order. So we need to manually sort, but it's disabled by default, and then it's supported by an option.
I see.
Yeah.
Okay, we have time for 2 questions.
Thank you.
Yeah, I was just wondering, what is preventing you guys from just implementing salting under the hood automatically?
You want an honest answer? Yeah, I mean, like it's basically like partial aggregation technique. So not all aggregation functions actually can leverage this technique. For instance, count or sum, you can just do the partial aggregation. But let's say, yeah, median or those things cannot be solved like that. So actually, we're working on streaming, manner execution instead of this sorting technique.
I'm curious to know what's in the 15 to 20%. Like, do you support multi-indexes on columns and rows, all the time series things that are in Pandas?
Yeah, so I assume you are talking about the API coverage, right?
Yep.
Yeah, so there is actually a pretty detailed documentation link that let me see whether I can just click on it right now. So a lot of the things are things like, sorting the time index. So you can see that for each, on this page over here, there are multiple sort of different types of API. Then you can check whether one is implemented or not. And then there is also something that has like a P over here, like what is implemented, but what are some parameters that are missing. So if you are curious, what are not supported, then this will be your documentation to refer to. But you will generally notice the trend of like, a lot of the time delta indexes that are not supported. And then there are also some things more about like doing some count for like median. It just doesn't make sense because for example, when we keep going back to the example of median, it's because you really do need every single row to be sorted to find a median. And if you want to speed that up in a Spark data frame, that's just no way, right? That's why in Spark, you can only do an approximate median.
Okay. Thank you again, the speakers.
So thank you all for coming out.
Thank you.